MAP4C 6.6 exponential equations. An exponential equation is an equation with the left and right hand side where the variable is in the exponent. And we have solved equations typically using opposite operations. In order to be able to get the x variable to be the base in this exponential equation, we don't have the opposite operation for that. Something does exist called logarithms, but we're going to learn an algebraic technique to be able to solve this type of equation. So, notice that in this example, we are trying to write using a common base. So, right now the base is 2, this is the power or exponent. The base is 8, the power is 1. So we can express 8 as a power of 2, so that we have the same base. So 2 cubed is equal to 8, and then if we have 2 to the x is equal to 2 to the 3, the only time that 2 to the 3 is equal to 2 to the x is when x is equal to 3. And I'll justify it using this image. An exponential equation produces, or a relation represented graphically, is a positive increasing function at all times. Even though there's a horizontal asymptote on the x-axis, it is still constantly increasing at all times. So, the number of points where it is, say, for example, 2 to the x is equal to 8. Let's say that this right here was the height 8 on the y-axis. There's only going to be one instance where the exponential curve goes past y is equal to 8 for this value of x. So what we're doing is the following. If a to the m is equal to a to the n, then m must be equal to n. What does that mean? This is referring to this specific example here. 2 to the x is equal to 2 to the 3. The only time where these two will be equal is if x is equal to 3. So if the base is the same, we can equate the exponents. Let's look at some examples. 5 to the x is equal to 5 to the 6. The only time that that will happen is when x is equal to 6. So we equate the exponents and then this equation is solved. Next, 2 to the power x is equal to 32. So if we can express 32 as a power of 2 so that we have the same base, that would be 2 to the 5. And therefore, the base is the same. The only time that these would be equal is if their exponent is the same. So let x equal 5. The equation is solved. A more complex example, 7 to the 3x minus 4 is equal to 49. Step 1 is get a common base. So 7 is the base on the left-hand side, and 49 is equal to 7 squared. At this point, we have the same base. We can equate the exponents. We have 3x minus 4 is equal to 2. And we can solve using opposite operations. So to get the variable x by itself, we can add 4 to this side and the other side. That will bring us to, once we simplify it, 3x is equal to 6. The opposite operation is divide each side by 3. And our result is 2. You can always check at the end of your calculation with substitution. If this is the solution of the equation, then substitution into the equation should balance the left and right hand side of the equation, or satisfy the equation. 3 to the 5x plus 8 is equal to 27x. Now, if we need to get the same base, 3 to the power 3 is equal to 27. Now notice that x is on the outside, so we have to apply the power of a power rule, which states 3 to the power 3 raised to another power. We can multiply those exponents. It would be 3x. Now we have a common base and we can equate the exponents, meaning the only time that this is true is when 5x plus 8 is equal to 3x, this statement here. Opposite operation, subtract 8 from each side. Then we are left with 2x is equal to negative 8. The opposite operation, 2 times x. So divide each side by 2. X is equal to negative 4. You can substitute and check your answer. Last example. We have 2 as our base. We need to express the right-hand side as a power of 2. Well, 4 is equal to 2 squared. Notice that this is in brackets and that we have to apply the power of a power rule again. But in this case, it will be with distribution. So 2 times 3x is equal to 6x. 2 times negative 1 is equal to negative 2. Great, we have common bases, therefore we can equate the exponents. And 2x minus 5 is equal to 6x minus 2. We can distribute 2 through the bracket, 2x. 2 times negative 5 is negative 10. And then we collect like terms. Notice there's x terms and numbers just by themselves. So, to the left-hand side, we'll take away 6x from this side, take away 6x from this side. We will add 10 to the left-hand side and add 10 to the right-hand side. This is our result. Simplify their values by adding them together. This is negative 4x, and this is 8. Negative 4x is equal to 8. We have one term now, and it's being multiplied by negative 4, so divide each side by negative 4. Our result is negative 2. You can substitute into the equation to check. All right. Another technique for solving exponential equations. This is kind of like guessing and checking, but it's a systematic technique, meaning there's an algorithm, a series of steps to get to your answer. Use systematic trial to solve 3 to the power x is equal to 7. Notice that this is not an even power of 3. If we were to multiply or try 3 to the 1, that's 3. 3 squared is 9. That's actually in between those two values. And if we know, looking at x and y, which is 3 to the power x, we're trying to get as close to that value as possible. What value, or what exponent on 3 is closest to 7? We already said that when x is equal to 1 and x is equal to 2, it's bounded by 3 and 9. 7 is between these two values. It appears to be closer to 9, but what you can do is use the midpoint of 1 and 2. And based on the value, when you substitute in 3 to the power 1.5, you get 5.20. 5.20 is not that close to 7. It's between 5.20 and 9. So we're going to look for some solution. We know that it has to exist between 1.5 and 2. So what we can do is look at, because we've taken one decimal place, we'll look at each tenth, meaning one decimal place. So 1.5, 1.6, 1.7, 1.8, until we exceed the value 7 that's desired. Here, 1.7 and 1.8, those values of x contain the solution that we're looking for. We're looking for when is this equal to exactly 7. We're going to apply the same technique, but now to the hundredths place, or to 2 decimal places. Looking at our solution, we know that 7 will occur between these two values, so we use the midpoint of 1.7 and 1.8. We can add them together and divide by 2. You'll get the value 1.75 as the midpoint of these two numbers. And we get 6.84, which means we still need to go higher, because it's an always increasing function, or graph, to get our solution. So we'll get a little bit closer by going 1.76, 1.77, 1.78, and it appears that 1.77 is the closest that we can get to the nearest hundredth or 2 decimal places. And our last example, and again, this is an approximate solution, so remember, that's why there's a dot above the equal sign. So this technique is helpful whenever you have an image of the graph. If you were to graph 2 to the power x, that is represented by this curve, and the line y is equal to 5. Y is always equal to 5. That's the equation of that horizontal line. Approximate the point of intersection. So if we look here, this goes to the x-axis at about, let's see here, 1, 2, 3, 4. That is about 2.3. It appears to be a little bit over half. So, that being said, this is a graphical solution to solving the equation. Good luck.